Okay, so it is my pleasure to introduce Susana Gomes, was kind enough to accept our invitation to deliver a talk in CIM's Colloquium of 2025. So Susanna is an associate professor in the University of Warwick, and as main research interests, she has modeling and control problems described by partial differential equations with relevance to applications in physical life and social sciences. In particular, today she will talk to us about the mathematics of opinion dynamics on evolving networks. Okay, so Sana, again, thank you very much, and the floor is yours.
Thank you. Can you hear me okay? I'm not trying to share my screen because I should have done this first. But anyway, okay. Just moving the Zoom thing around so that I can see faces. Okay. So yeah, as George said, I'm going to talk about opinion dynamics, which is something that I just started working on very recently, actually. This is supposed to be a video. There you go. So this is work that we've done in the last 2-3 years, and there's still a lot to come. I wanted to put some partial differential equations here, but I didn't think I'd have the time. So if I have some time in the end, I can talk a bit about more recent things. So this is sort of a summary of what I'll talk about, an introduction of why people care and what's known so far, and I'll try to sort of explain where I come from and why I decided, after spending a lot of time working in partial differential equations and control of other things, why I started doing this. And then start talking about what I've actually, I think I can have a pointer. There you go. What's actually my work, which is opinion dynamics on networks and how to control this. Okay, so just as a quick summary of why people care about opinion dynamics, this is relevant for all sorts of things like election and polling results, or actually I try to stay away from manipulating people's political choices and things like that, but there's a lot of things like consumer choice behavior, or how people interact in social networks and how that makes people's opinions change through time, or even how to connect people in such a way that they can cooperate or not in some movements, with examples of things like, will I cooperate with my neighborhood's plans of recycling or doing something that's environmentally friendly? So the point is, people would like to predict the collective opinion rather than manipulating each person, knowing what a group will do as a whole. And there's a lot of models and approaches that exist. And in particular, people in computer science and social sciences have been working on this for a very long time. And recently, a lot of mathematicians, or at least mathematicians I know, started being interested in this. And the reason for that is that I in the past worked in communities of interacting particle systems, so people trying to model agents, and agents can be particles, atoms, birds, people. And for large populations, what people tend to do is then take the mean field limit, meaning you set the number of people to infinity, and you can get a partial differential equation for what the group is doing for the density or the probability density of what's going to happen. And so a lot of people recently have come across these models of opinion dynamics that come from computer science, and taking this limit as the number of particles going to infinity and not really thinking what this means, or if this is even realistic. So this is sort of where I'm coming from, looking at these models, trying to make them a bit more realistic, and hopefully that's what's going to come across in this talk. Okay, so here's sort of a list of things that I can think of that can change the type of models that we have. And again, some of them are more common in mathematics or computer science. So one of the first things that you need to think of when you're trying to model opinion dynamics is, what's my opinion space? Am I doing a yes or no question type of referendum, or am I doing a level of agreement where I can consider a continuous opinion space from I completely disagree to I completely agree with everything else in the middle. And in terms of continuous and discrete, you can also think, how's my time evolution? Like, do I fix a particular time and then just change things every hour or every day, or is my time continuous? And then more interesting things are, do I only have one opinion or will I have multiple opinions? How do they interact with each other? When I interact, do I interact with just one person or a group or everybody else? And also there's different types of populations. For example, you can model a homogeneous population, like a whole population of a neighborhood, or do I have leaders? Is there somebody that can influence my opinion just because they're a group leader or they're my boss or something? And on top of all of this, we can also add noise. So for today, I'll start with, I'll always consider continuous opinion space. So everyone has a continuous place where they can have opinions. And most of the time it's going to be continuous time. And at the end, I'll talk a bit about what we're doing in terms of high dimensional opinion spaces and heterogeneous populations. Okay, so as I said, for most of today, I'll consider a homogeneous population. So everyone has the same level of information and the same level of things that they can do. My opinion, I'm person I have opinion xi that lives in -1, 1. So -1 is completely disagree, +1 is completely agree. And agents will interact with each other based on an interaction rule. This function will come up a lot later, and this will make more sense in context. But the most common model that at least mathematicians look at is I will talk to you and consider changing my opinion based on what you're telling me if your opinion is close enough to mine. And by close enough, I have some threshold, capital R here. I'll also introduce a social network, which is modeled by a graph that has an adjacency matrix with some weights, which I'll explain when the time comes. And except for a couple of cases that I'll show later, there's no noise in what's happening. So everything's deterministic. Okay, but to start with, I'll talk a bit about where this model started. So usually the first model that I sort of know of, or that people tend to look at when looking at this, is called the voter model, which is not what I'm going to show now. But in the voter model, you have an opinion of 0 or 1, you interact with somebody, and you change your opinion with some probability based on the other person's probability. We started 5 slides from now or something like that. But this was actually, so this was a PhD student's project, and this was actually how I wanted him to end his project. And it ended up being the beginning. So he was in a conference presenting the work we did that will come a bit later, where everything's continuous. And somebody told him, but do you really think that this is an accurate representation of how people interact? Because you'll see later, but most of the models, what they do is they assume everyone interacts with everyone else all the time. So you can process information very quickly, and that's not realistic. And that was one of my problems with this. So we wanted to sort of show, is this a realistic thing? So that's what the next few slides are doing. So in these types of models, at the very basic level, you have a population of, say, n individuals, and at every time step, which can be 1 day, 1 hour, wherever, we haven't defined the time step yet, you select the person I whose opinion will be updated, and then you select the person J with opinion xj that will talk to this person. And then based on the two people's opinions, xi and xj, you check the distance between the opinions, and you assign, using this function phi, you assign a probability that the opinion of person I will change. And so at the next time event, your new opinion is either going to stay the same, or it's going to move a little bit towards the opinion of the other person that you talk to. And then if you want to simulate this, and this is called the Defwant model. Defwant was the person that actually came to my student and asked him, are you sure this is okay? All you need to do is define this probability function Pij and the step size mu that measures how much you'll go towards the other person, and obviously the time age. So you can do this and simulate. I don't know why my videos don't start from the beginning, but this will restart. You can simulate populations interacting with each other, where at every time only 2 people interact with each other. So in this video, we start, I think it's about 20 people, and the non-black dots are the people interacting, and then red, I think red means that they don't change opinions, and blue means that they change opinions. And eventually you can model things like this. And then you can start with a lot of random initial conditions, and obviously at every time step, there's different people changing their opinions. And so what you do is you do this a lot of times, and you take averages, and you get some sort of measure of what the behavior of this system is going to be. So the problem with this is that this actually ends up being a bit computationally expensive. So if you want to, I mean, obviously it's not very, very bad, but if you want a population of, I don't know, 500, say, so this was 20, this was not too long, but if you want large populations, you need to wait on average more than, well, at least more than 500, but much more than that, so that every pair, actually you need to get the pairs to interact with each other. It takes a very long time so that everyone sees everyone else. So this can take a very, very long time. And this is why now mathematicians consider the differential equation models that I'll show in a second. But yeah, every realization you have will have a different behavior, but on average, this will tell you, will this population reach consensus or not? And if it does, where does it end? If it doesn't, what happens? And you can see that you have like people merging here in the middle, but then there's sometimes people that never talk to anyone else, and so they stay in the middle and never change their opinions. So what then we wanted to do was, okay, let's see how, if this actually corresponds to the mathematical models that we actually use. And so to do that, what's possible is we can actually measure on average when an opinion is updated, what's the average update? So what's happening on average to me at every time step? So the expected value of my next time step, given my current time step or everyone's current time step, and the covariances. And if we choose first of all, the time step, so this age, like this variation on time, and the step size that I do correctly, then we can actually pass to the limit and see that the expected change of opinion for person I is given by this probability function Pij of x times xj minus xi. So I move towards the opinion of person j on average with probability Pix, and the covariance, the aij's are always 0, and the covariance gets this expression. And so what's to say here is that actually, so if, so n is the number of individuals, and age is the time that we advance. So the step size is the number of individuals times age. So what this is saying is if I take age to 0, so if my time step is very small, so if I can talk to people very fast, but then also if age is very small, my step is very small. So if every time I talk to someone, I change my opinion a little, but not too much, then this goes to 0 because age goes to 0, and we remain only with the expected update term. So this results on the Exelman-Krauss model, which is the mathematical model that everyone I know has been using. And it just says that the derivative of my opinion with respect to time is an average of me going towards the other people weighted by some probability function, Pij, which I'll define in a moment. But this was at least as far, like these types of results are known for general Markov chains, but nobody's ever, as far as we know, nobody's ever looked at this in the context of opinion dynamics and these types of things. So it was nice to at least have some confirmation that this mathematical model that everyone's using, in the right conditions, I can talk to people fast and I don't change my opinion very much. give us the model that everyone likes to use. So yeah, so this is just a video or a GIF of what happened. So what's happening here is I am making age smaller. So I'm making my time step and my distance a bit smaller. And the dashed lines that are not moving are solutions of the ODE system that I just showed. And the wiggly lines that are moving are the dynamics on average of the agent-based thing where at every time step, one person talks to somebody else and changes. So obviously, if my time step is very big or if my step is very big, then these lines don't agree. But once the step is small enough, then the agreement starts being very nice. And eventually you actually get the lines to overlap, which was really nice. So this shows that you can actually, in the right scenarios, you can model populations, even if they're not very large. You can model the populations using this system of ODEs, which this one takes seconds to solve in a computer, while the agent-based one takes much, much longer. So this was good. So some things to note about this model. So that this probability function Pij determines what the interacting function can be. And I haven't said what it is yet. It's going to be that function phi that I showed earlier, but it can be anything else as long as it's Lipschitz continuous. And you can, in principle, show existence of solutions for the system. In the example I showed you, I said that everyone could interact with everyone else, but you can choose whether only one person changes their opinion, whether both people change their opinion, or you can put networks on this. And if you do this at the agent level, then this you can do exactly the same thing and end up with a similar equation, but with where the weight, this 1 over n here, might be different. You can also add noise in a lot of ways. You can say my noise is just affecting, so like there's already some noise in the random choice of who interacts with whom, but you can then add noise on how much I move towards that person. I can add noise on so the step size, or I can just add noise after I update my opinion. You can add noise on what you see from the other person, and this all ends up with a system that looks like this one, but might have noise on the right-hand side. And that noise may or may not depend on the opinions, depending on the rules that we use. Which is, again, another thing that people tend to just add noise and not really think about where it comes from, but now we know what type of things leads to different types of noise. And yeah, so this is just me saying that we can add a social network underlying to this, so that the person you interact with is randomly chosen from your neighbors rather than from everyone else, and we get the nice model. Okay, so this is just a bit of a justification of why these models are at least a little bit realistic. I'm not claiming, and I won't claim today, that people actually act like this, but it turns out that a lot of models in social science do think that this is sort of how people interact. So the model that I just wrote, as I said, it's called the Hegselman-Krauss model. I think it was proposed by Hegselman and Krauss about 25 years ago. And I just rewrote it again with this function phi. So you can think of this function phi in a lot of ways. It can be how much attention do I give to somebody's opinion. It can be how much that opinion influences me. We are also looking at, like, not in this talk, but we've been looking at how much discomfort an opinion creates. So in the case where you have more than one opinion evolving at the same time, you might not want to evolve your two different opinions to something that's contradictory. So the example that we sometimes use is if your opinion is how much do I consider myself to be vegetarian, and then you have another opinion of how much meat do I want to eat. You don't want both of those to be one, because they're not they're not consistent. So we call that psychologists call that cognitive dissonance, and there's a lot of books in psychology that we've been reading, and you can incorporate a mix of these effects. So most of the time what people use are functions that look like this. So the one that the model was the model came from is the step function. So you are this function phi is 1 up to that level r that I listen to people, and then it becomes 0. But for purposes of existence of solutions to these systems, you usually just want a modified version of this. Sometimes it's useful to consider functions that are always positive, but then you just don't care too much about opinions that are too far. And there's a few other things like there's a lot of models that say, actually, it's better to listen to people with completely different opinions. And I'll show you what happens when you do that. So this is the type of behavior, I thought this was coming later, this is the type of behavior that usually you see. So with a typical function that is 1 and then becomes 0, what happens a lot is that you get to some sort of consensus with people agreeing, but a lot of the time you just get clusters. So you cluster with people that agree with something and a cluster of people that disagree. And it was known already, and it's well known that depending on what the radius that you listen to is, you will get a different number of clusters. It is also known that if your function is always positive, you eventually end up with consensus all the time. And here on the right, I have an example of the case that I said, that instead of listening to the people whose opinion is close to me, I'm listening to people who completely disagree. And this also enhances a bit of consensus usually. I think people's faces are in front of this. But yeah, so these two lines are a bit closer than these two lines. So even though everyone doesn't agree, they're a bit closer in opinion. So there's different people exploring different types of things with this. Okay, so this is sort of a summary of what I said of things that were known before for these models. So if you define the diameter of the system as the maximum distance of opinions between two agents. So for example, here you start with a diameter of 2, and then your diameter decreases until it sort of stabilizes into something that's about 0.6 maybe. And here the diameter is 0 and things like that. So if you define the diameter, you can show that it's non-increasing. So you will always, like, all the opinions will remain within the same window as they started. You never get out of your domain. And it's also known that the diameter converges to some value, so you'll always get a steady state or a stationary state, which may or may not be consensus. Yeah, I don't know why I said it's always consensus. It's not always consensus, but it is always consensus if your function is always positive. And the way you show that is that if you fix any epsilon, you can actually show that after a while, you can bound the product between the function phi and the distance of opinions by epsilon. So what this means is if this one is always positive, which can happen in some examples, then this one has to go to 0. So that would give you consensus. So this is usually how people prove that there exists a consensus steady state in this case. So yeah, this is what I just said. So if your function is bounded from below, then you know that consensus is guaranteed. But again, for a lot of the time, this is the type of analysis that people used to and still do in these types of things. They take a model like this, they change the interaction function or add something a bit more to it, and then they check, does my system reach consensus? And if it does, how fast does that happen? But there's not a lot of other studies in things like this until you start trying to control things. Even if you have networks, that's the type of thing that people do. And to some extent, this is all you can do, because even if you end up with something like this, depending on your initial condition, you can shift this a little bit up or a little bit down, and it's always gonna be a steady state. So you either have this one or you have infinite ones. So it's a bit hard to do much more than that. So what then people started to do, and we tried to, and this is what we actually built upon, is okay, let's make this more realistic by introducing a social network. So I have a graph. I'll show you an example of a graph in a second, with adjacency matrix that is weighted with Wij. So basically, Wij is 0 if people are not connected in the social network, and then it's non-zero if they are connected, and then different levels of Wij mean I am very good friends with this person or I just know them. At the moment, we just have them positive. Something you can do is make them negative. So I don't like that person, so I'm going to go away from their opinion. We haven't done that yet because one of the things that creates is the possibility that you get out of the domain of opinions, and you don't want to do that. And in this case, you normalize not by 1/n, but by the number of neighbors, just so that your averages are okay. And again, in this case, you can prove the same type of things. If you have a connected graph and you assume that your interaction function is always positive, then you know that you'll still reach consensus. It will be a bit slower, and there's a lot of research on diffusion in networks, like to find out what's the convergence rate to consensus in this case, but you can prove the same type of results. So this is just as a comparison. So we ran the same model. This is an Erdos-Renyi graph with, I think it was 500 agents. So it's a random network with some probability of people being connected or not. And so these were the plots I showed you before. So with a step function, the function that's always positive, and the function that you listen to the people far away from you. And what you see is that in general, the dynamics at the end of the day is more or less the same, with the exception that sometimes people don't talk to each other and stay with the same opinion forever. But what happens is that it's a bit slower. So this still reaches consensus, but before it came at around 50 something, and now it comes at around 75, 80, and similar to the others. So obviously, depending on the network that you add, you get different behaviors, and there's all sorts of networks you can do. And we just tested this one because it's, to be fair, it's the one that people use the most in the literature, but also it's like the simplest random network that you can. But you can do things like citation networks that have a different connection structure with people that have more neighbors and people that have less neighbors. In here, on average, everyone has the same neighbors, which is why the same number of neighbors, which is why the behavior is similar. Okay, so obviously you can do this for a lot of cases and for a lot of networks, but at the end of the day, from something like this, the best you can do is some I metric of do I reach consensus or not, or what's the behavior. So this is where the people from statistical physics started coming to this. And what people introduced was what they call an order parameter. So this is this Q metric here that is simply 1/n squared times the sum of the phi xj minus xi. So in general, if your opinions are close enough, this is going to be 1. If your opinions are far, they're 0. If everyone has the same opinion, this is always 1. So this sum is n squared. So this Q is 1. And if people don't have the same opinion, this is going to be smaller than 1. And so what you can see is that if you change the bounded confidence radius, meaning how far from my opinion am I willing to listen to other people, what you see is that you end up with this Q being very close to 0 because nobody's listening to each other. Everyone stays in their lane. And then this gradually increases and you get to a point where you have a plateau and then another plateau, and eventually this becomes 1. So this is sort of well known that if you're willing to listen to people with opinion about 0, I think it's the length of your domain divided by 3, I think, then you end up being in consensus. And then this here is about a half, meaning you have 2 clusters, and then you have a third with 3 clusters, etc. So 1/, this number Q is usually the number of clusters you have in your steady state. And then you can do things like you vary your confidence radius, so how much you listen, and you vary, for example, in this random graph that I showed you, you can vary the expected mean degree, meaning the expected number of neighbors that people have. And you can see that as you increase the expected mean degree, as you increase the radius, you go towards one. So the yellow region means consensus, the blue region means completely disagreement or just uniform distribution, really. And then there's a region in the middle where you're somewhere in the middle. And again, these plots are seen a lot for this types of things, and you can vary other things. But this was a good metric to see what's happened. So this is where we said, okay, in real world, networks also evolve in time, right? I connect to people, I start following people that I agree with, I stop following people that I don't agree with. And so we started to try to introduce some rules of how people interact with each other and how that influences their neighbors. So we allow for the edge weights now to evolve as well. So we let people connect to each other if they agree and disconnect if they don't, or at least decay on the weights. And so we end up with a system like this. So the first equation is the same as before. I listen to people that are my neighbors and are close enough to me, but then I let the weights of the edges, so how much I listen, I consider the friendship of that person, evolve according to this. So if I agree with people, I multiply my I let my weights increase with some function f plus, which is positive of the weights. And if I disagree, then this is 1 because phi is 0, and I multiply the weights. I let the weight decay with some function f minus. So we tried different types of weight dynamics. The first one that we tried was what we call logistic weight dynamics because it's just a logistic function. So if I agree, I let my weights increase with this rate, and if I disagree, I let them decrease with this rate. My favorite one is called a friend of a friend because basically it allows me to, if I know you and you know somebody else who agrees with me, you can introduce us. And so we create edges between people. If you let this run forever, you end up with a complete graph. So there's things we need to look at, but I thought this was sort of the most realistic type of thing that we could do. And we also considered something called memory weight dynamics. So you just multiply by, you tend to want to stay with the edges you started with unless something happens. So we can evolve the same type of dynamics with this network evolution. So this is a case where there was no network. So where everyone was connected. If you add a fixed network that doesn't change with time, we see what I said before. So things just happen slower, but you end up with a similar type of situation. And then with different weight dynamics, you then get either closer to the beginning or you get something completely different. So it really depends on what you're doing. Then you can play the same game. You can change the expected degree. You can change the way you listen to people and see what that does to consensus. So in general, so things like the logistic weight dynamics, which just tends that what it tends to do is either all your weights become 1 or 0 because those are the fixed points that we just give to the system. It just increases consensus to some level. But then the others just actually, in some sense, sort of decrease it a little bit if you see that there's a dip that was missed. So this already changes the behavior of people a little bit. You can also think about, at the moment, I'm letting the two things evolve at the same time, but you can do things like I can change my opinion faster than I change friends, or I can change friends faster than I can change my opinion. And this is very common in things like cooperation, things where your opinion is I either cooperate or don't cooperate, and these are my neighbors. You can actually, like if you're thinking about your neighbors being actually your real neighbors, you're probably not going to move house very frequently. So this things happens a bit slower. And actually they see things that to me look a bit like a phase transition, but I haven't had time to explore that. The bottom plots, I didn't say much about them, but what they're saying is how long it takes to get to the steady state. So the gray, where's my, yeah, so gray is fast, yellow is very slow. And I think what the main thing to say about these plots is that actually in this place where the behavior changes, like if you overlap this plot with this plot, this line here is what's going to be this yellow. So the part where you're changing from everyone goes to consensus to everyone doesn't, something happens there, which is also very similar to what happens in phase transitions. If you know about this, like the behavior gets much, much slower. We actually really had to solve the dynamics for a very long time to actually see the steady state, which is interesting. Okay, so at this stage, we know we have an opinion dynamics model that may or may not be realistic. We have a model to how the network changes. And so because my background is in control theory, we wanted to see what we can do in terms of controlling what happens to these systems. So again, I'm just writing the system here again. And what a lot of people do is, if my system doesn't go to consensus, I want it to go to consensus. If my system already goes to consensus, I want to make it faster. And there's also some works on how to make sure that the consensus is in some point that you want. So what people usually do is they put just some right-hand side in the function. This is my control. And this assumes that I can control everyone. This just says somehow I can talk to everyone and make them change their mind just by, I don't know, putting a TV ad on or something like that. We thought that was a bit unrealistic. So we did something that sort of still is a bit realistic, but it's a bit more doable, I think, which is instead of controlling an agent directly, we're controlling the social network. And if you think about, I don't know, what Twitter does, what Facebook does, is sort of you get targeted ads. You see more people more than you see others. So that's something that they're already doing somehow. And so what we're doing is we're going to put a function on the right-hand side of the weights rather than on the right-hand side of the agents. So if you do that, you need to make sure that the function has the right shape. So if you don't control your network, then the control stays the same. So because this is just a dwdt. If your weights are 0, then your function needs to be positive because you don't want them to go negative. And if your weights are 1, you want the function to be negative because you also don't want it to go above 1. So this guarantees that the weights stay between 0 and 1. And this is like the type of thing that we're using or we used in this paper. So you say that your function of the weights and the control is some function s, which is this quadratic function here that tells you how much influence you have on the weights themselves times some L minus W, where L is some function that tells you how close you want to be to the weights that you are. So this sort of stops you from changing too much. So it's the product of these two functions here. So what we wanted to do here was, okay, so if we have some initial conditions, can we find a control U that brings the whole population to consensus at some targets X star? Okay, so the type of questions that we can ask is, does the control exist? If it exists, how do we compute it? How well does it work? And how close can we get even if the control doesn't work? So the first thing we could prove was if we have what we call your usual nice interaction function, nice control, so everything is continuous and differentiable and everything. If we pick a desired consensus point X star, then we know that there exists some initial conditions and some initial weights for where we can't control, actually. So it's not always possible to find a control. There you go. So this is what can go wrong. So the first thing, in these two plots, the dashed line here is the desired consensus point. And the things that can go wrong is if your opinions evolve to some point where basically you end up far from each other by the dynamics that you have, then you're not interacting anymore, so you will be far away. Or if your target opinion is not inside the desired interval. So if you think about what's happening here, basically what's happening is that the dynamics of whatever's happening in these two examples is faster than the control. And because of the way that we have our functions and the controls, once this dashed line is outside of the interval of the diameter, then we can't reach it. Or if the diameter is bigger than the opinion, then the bounded confidence, then you also can't reach consensus. So in general, for a control to work, you sort of need to prove that this doesn't exist, that this doesn't happen. Okay, so in theory, then what you can do is, okay, if I know the initial conditions and I know the initial weights, then I can choose a consensus target, right? So here, 0.25 didn't work, but maybe if I put it 0.2 or something like that, maybe I could have acted fast enough. Okay, so the idea of how to prove this is we first reorder the agents based on their opinions, which we can do without loss of generality. We define the minimum and the maximum. And we define something called an R chain if the distance between two consecutive opinions in this ordered vector is smaller than R. And so if we have that, and if we start with an empty network, meaning nobody's talking to anybody else, and our initial state is an R chain, so everyone has their own opinions from the beginning, and then we assume that there is some control value so that these two functions are positive, just for the sake of the proof, then we can show that if the control can be used to create new edges, then there exists a control that reaches X star. So basically, if our network is not connected, so if we start acting on the network from the beginning, then we can create a network that will make the opinions evolve towards what we want. Okay, and the idea of the proof is you find the two people that are closer to the opinion that you want, you bring everyone else to them, and then you bring these two together. And you can do that as long as the R in that R chain is smaller than the opinion interval that you're happy to move on. Okay, so the takeaway from this result is that if the control acts quickly, then it can prevent people from crossing that target opinion. And so you're always going to be in a situation where the target opinion is in the range that you can reach, and the distance between opinions is so that people move. Okay, and this was, I'm not sure if I need this, but this is basically the smaller, if this function is 0, then we define the smallest root by this. This is for the next result. So this is a lot. I'm not going to say a lot about this, but the point of the next result is that if I have this bounded confidence function, it needs to be smooth so that we can prove things. We have some initial condition, and we have some target that's within the initial conditions. We assume the same things on the controls, and we assume that there are two numbers that bound these controls. Then if this S minus is sufficiently large, then we can always find a control that makes it reach consensus, even if the network wasn't completely disconnected. So again, this is a lot of words, and this is what it actually means. So if the opinion is in the interior of the initial points, if the initial opinions are not already in a cluster, and the control can add and remove edges anywhere in the network, then if it acts quickly, we can make consensus happen. So this is an example of this working, and you can sort of see that this is what's happening. You're bringing the people furthest away closer and closer and closer to. So the proof is actually constructive. They're getting closer to the next person, and then they all come together to the point that you want. Okay, so this is, okay, the control exists, we can find it. Can we find this in an optimal way? I'm almost done. So we just to do this in an optimal way, what we're trying to do is we have a cost function. We want our controls to be as little as possible, meaning we don't actually want to change the social network a lot because that's not reasonable. And we want our opinions to be as close as possible to the consensus point, subject to the differential equations that we have. And then we're saying also, we not only want it to be small, we also want it to be capped at some maximum and minimum points. I wrote the adjoint system here, but we don't really need this. But the point is, you do the usual thing when you do constraint optimization. You define a Lagrangian function or non-Hamiltonian. You take derivatives, you get a forward-backward system that you need to solve. This is just to say that in the original system, you have n agents and you have n squared weights. So that's a n plus n squared size system. And this is twice as big as that. So it does take a while. But the point is, if we choose these two functions, which are the ones that I showed you before, you can actually get an analytical solution for this that says my control is the maximum that I allow it to be, or the minimum if some conditions happen, or zero otherwise. So I'm not doing anything if some conditions here that I can prove analytically what they are already met. And if they're not, I'm either going to add an edge or remove an edge. And to see this, so this is the result to compare with this here. So if you look, sorry, to compare with this, which was the just basic construction thing, with an optimal solution, you see a similar type of behavior, but this is much smoother and much nicer. And what we're doing with the network is this. So in this case, so every dot, this will restart in a second. So every dot is an edge. Every dot is the opinion of person I and person J. If the dot is gray, I'm not doing anything to the network in that pair. If the dot is orange, I am making the weight of that edge increase. And if it's blue, I'm making it decrease. So what this is doing is sort of getting people far away to connect to each other, and people that are close, but their opinions aren't changing the other person, then you just remove the edges because they're not doing anything. And after a while, you actually end up in the desired consensus point, which in this case was just 0.5. I'll just let it start again so that you see how it looked like at the beginning, because then the evolution is not super interesting. It's just you can actually see patterns on what we're doing. I did not realize that this was so slow. Let me see if I can start it. No. I need to work out how to restart videos on PowerPoint. That's the problem of this. But yeah, I'll just let it restart and go to the next slide, which is, I think, the last slide anyway, because I think I'm running out of time. I don't think this wants to restart. No. Okay. Anyway, so yeah, there's a lot that we know now that we didn't know before. But again, this is all very unrealistic still. And I mean, to be fair, it's a bit scary when it stops being realistic. So I'm unrealistic. So I'm happy for it to continue being unrealistic. So one of the things that we're trying to do, and it turns out it's harder than you would have thought, is to have multiple opinions influencing each other. So you can, these are some experiments that we did. Again, the video started from the end. There you go, restarted. So the right one has noise, the left one doesn't. And usually then what happens is you have to decide how the opinions influence each other. And you usually do this by a correlation matrix. But then if you don't do this in a smart way, what you end up is with the steady states aligning with the eigenvectors of these matrices. So you're not doing anything much new. And then if you have noise, then things will eventually join together and things like that. But there's some things we can do, and we're trying in this area. Another thing that people, again, in my field like to do is to take, okay, now I take the size of my population to go to infinity. This is easy and well known how to do if you don't have a social network. So if everyone talks to everyone else, this is easy. The moment you have a social network, the assumptions go away. But if you do that, again, a video that started from the end, it will restart in a second. If you start with you can obtain a PDE for the probability density of people having certain opinions or not. Let's see if I can restart this. There you go. So you start with a uniform distribution, and you can evolve the probability distribution and the agents, and you'll see that they will cluster where the PD is predicting that they will cluster, which is quite nice. But as I said, this is well known how to do without a social network. The moment you have a social network, you sort of have to take the limit of the social network as the agents go to infinity, which is like there's a lot of people working on this. It's something called a graphon, which is a differential operator that depends on the network. But then it turns out that actually, for most of the types of networks, it doesn't, in the limit, you get the same thing, and that's not the same thing as you see in the agents. Yeah, as I said, mean field limits, including social networks. And we want to make this more realistic. So for example, we don't want to act on every edge or on every agent. We want to just have one person lying or something like that. We have a few students working on this now. Okay, and yeah, at some point you sort of want to look at agreement with data. Finding data for these things is very hard because you need a lot of data in time, and we're still working out what the best way of doing this is. Okay, so just to finish, this is work with my student Andrew and my colleague Marie-Therese. These are the papers that we based this on. We have a few new papers that are more PD oriented, but they just came out a couple of weeks ago, so I didn't have time to add it. And yeah, I hope this was interesting, and thank you for your attention, and I'm happy to answer any questions.
Thank you, Susana.
I'll stop sharing for a second.
Thank you. Very nice presentation. So are there any questions?
Well, I have a curiosity. So if you would have, I was wondering if, so you have the weight matrix. So is there any relation between, of course, in some of the models you mentioned, this weight matrix, the weights are also evolving.
Yes.
But supposing they are fixed, the speed at which you get convergence, supposing you don't change the weights, my question is if the speed at which you can expect this, how do you say, the
Consensus. Yeah.
consensus, it can be detected by some spectral measurement
Yes.
of the matrix.
Yeah, so you define the graph Laplacian, which is
okay
of the graph, and I think is it the second eigenvalue that tells you how fast?
Or the gap between
the spectral gap tells you
yes,
the rate of convergence. Yes.
nice. So, and if you have, if you now let the weights change in time, would there be a way of trying to relate what's happening? Because as you change the graph or the weights of the graph, the spectral measurements, they change as well.
Yeah.
So would there be a way of keeping this relation, this kind of updating the speed as along with changing the spectral gap of the matrix?
We haven't tried to do that. It might be possible. I guess with some of the with the logistic weight dynamics or the memory weight dynamics, because it's simple, I think it should be possible to get an expression for that. I just never really looked into it. That's an interesting question, actually. Thank you.